want to open up your practice exercise booklets to page 26, exercise number, page 13, exercise number 45. Exercise 45, you may use your calculators for these. And kind of one big problem that sort of kind of goes different directions here. But you may use your calculators for this. Get some practice with a word problem. By the way, on that second problem, you want to think back to algebra class on that third problem. All right, you may begin. And Jamie just skipped to about 5 minutes in. When we get done with this, since I forgot to give you your practice exercise booklet. Exercise 45. got another minute or so to keep working. Put your pencils down even if you're not finished, and let's go and see how we did on these. Quentin was first. Quentin, it says that Heather cared for the Turner triplets for 5¼ hours at the rate of $4 per hour. The Turners won that one. Anyway, how much did she earn? That's not much money for a whole lot of time watching triplets. Anyway, how much did she earn? Good, really straightforward. You multiply 4 times 5¼ to get $21. Very good. On the next one. Heather spent 2/3 of the money that she earned caring for the triplets. But then she lost 3/4 of the money she had left. So how much money, that's special, how much money does Heather still have? Good, $1.75. On this one here, we first of all need to realize that she spent 2/3 of or times the $21 she'd made, right? Based on the first problem. Which means she spent $14. How much does she have left so far, class? $7. But then she lost, somehow, 3/4 of the 7. And so you multiply that out, you end up getting $5.25 she lost. We'll subtract that from the 7, there's your $1.75. Here's the fun one, here's the algebra problem. The money that Heather has left, now as soon as you got the $1.75 for the last answer, is in nickels and dimes. That's rough. She had 5 more nickels than dimes. How many of each coin does she have?
$10, 15 nickels.
All right, so what we want to do here is we want to say, I know she's got $1.75 or 175 cents. She has, well, I don't know how many dimes, but she has 5 more nickels, correct? Every dime is worth 10 cents. Every nickel is worth 5 cents. So if you add the value of the dimes plus the value of the nickels, it will give you the value of all the coins, 175 cents. And that's how you'll get 10 dimes, 15 nickels. Do you remember that number, value, total value from algebra class? All right, Heather gave all the money she had left to her Sunday school class. What percent of the money she earned did she give? And find the answer to the nearest whole percent. 8%. Great job. Remember, she made $21. So this $1.75 is what percent of the $21? Well, is means equals. What means x, of means multiply, 21. You're just going to divide away the 21 from both sides. Comes out to 0.0 something, rounds to 0.08, so 8%. By the way, is that a tithe, class? No, what did God say a tithe is? At least 10%. So now, granted, she gave everything she had left, right? I mean, it's just she lost a bunch of money, and maybe she was planning to give $2.10 at least to the Lord and just wasn't able to because she lost too much money. But I think this is one of the reasons why God wants our first fruits, right? So it's like, well, I'll plan to give this to the Lord, but I'm going to spend this first. And I guess the moral story is give to God first.
She's babysitting them. That probably also means she's probably like a teenager too.
Oh, so teenagers don't have to tithe?
If they don't have a job, I don't think they have to.
Well, she had a job. She babysat, right? So she made money. My kids make money. Make money. That is, they get money for birthday. They tithe. They're 3 and 5 years old, they tithe.
10% of their birthday money goes.
Mm-hmm. Absolutely. Yeah. 'Cause that's what God says he wants, 10%. The first 10%. So that's what they do. So anyway, good because that way God will bless you, right? That's the reason you do it. It's an obedience to God, and so God will bless you. And in various ways. It won't always be monetary, but I do believe that's one way he blesses. But anyway, great job on that. Genesis, you also got them all done. Did you get them all right?
I got one wrong.
Which one?
The algebra.
The algebra one. Does it make sense now? You remember it now? All right, normally we did 3 columns, right? The number would be x and x plus 5. The value would be 10 and 5. And so the total value would be 10x and 5 times x plus 5 and so forth. All right, anyone else get all the ones you did right? Maybe you didn't finish them all, but all the ones you did you had right? Any questions on these? All right, kind of a diverse set of problems here that kind of built on each other. So a little of everything there. All right, let me go and collect those from you. And while I'm collecting, let's review some things we've talked about recently. Concurrent lines. What are concurrent lines? Ethan.
3 lines that intersect. Or 3 lines that point.
Good, 3 lines that intersect at the same point, or more lines, right? But generally, at least 3 lines that all intersect at the same point. And we talked about 4 sets of concurrent lines in triangles. One of the sets of lines we talked about were the medians of a triangle. It begs the question, what is a median of a triangle? Kendall? It does bisect a side. Where does it go from, though? Because there's all kinds of, like, for instance, if I drew a triangle and I knew that this was the midpoint, I mean, that could bisect the side, right? But it's not a median, because a median specifically goes from a vertex to the midpoint of that opposite side, right? So the vertex to a midpoint would be a median. What about a line that goes from a midpoint to a midpoint? We said that's not a median. What do we call that line, Ethan? From a midpoint to a midpoint in a triangle. It's not a median. No. Audrey? We call it the no-name line, because it doesn't actually have a name. It's not an altitude, it's not a median, it doesn't even have a name, which is called the no-name line. But it is special, right? What's special about the no-name line? Back to Ethan. Kind of tell by looking at it that it is...
Isn't it have to go parallel to the third side?
There we go. It's going to be parallel to the third side. That you can kind of tell by looking. You can't necessarily tell this as easily by looking, Chris. Do you remember the other thing special about the no-name line? It's half the third side. Good. So it's parallel to the third side. It's also half the third side. So that's the no-name line. But with the medians, coming back here, lines that go from vertex to midpoint, we said that all of the medians will meet at the same point. What do we call the intersection of the medians, Genesis? It's actually the true center of the triangle. But there are 4 centers we talked about. So which one is the true center? The centroid. Good. The centroid is where the medians all intersect. We also said, Quentin, that the angle bisectors all have to meet at the same point. Where do they meet? The in-center. Remember, angle bisectors are equidistant from sides. So the in-center is equidistant from all the sides. You put a little circle inside the triangle. We said that the altitudes all meet at the same point, Kendall. Good. Remember, straight up and down altitude, right, or straight across altitude would be the straight orthodontist, makes your teeth straight, so orthocenter, if you want to remember it that way. And the last one was the circumcenter. What lines meet at the circumcenter, anyone? Perpendicular bisectors. Good. So perpendiculars, for instance, or altitudes meet at the orthocenter, but if the perpendicular bisectors would be the circumcenter, and just the plain old bisectors or medians would be the centroid, and then angle bisectors at the incenter. Make sure we're keeping up with those. And then yesterday we began looking at some axioms that I told you for the first time, don't memorize, but think them through. Have some paper out real quick. And I want you to maybe jot some numbers down and reason through these things real quick as I ask the questions. So I'm going to give you a moment to think, and then I'm going to ask you the question. Remember, the from comes first. When you're from, that's what's got to go on top or go first. If we were to add equal quantities to unequal quantities, if we were to add equal quantities to unequal quantities, We know that the results will be unequal in the, wait a moment, class? Same order. If you add equal quantities to unequal quantities, the results will be unequal in the same order. So that's kind of how you jot it down. Let's do another one. If we were to subtract unequal quantities from equal quantities, if we were to subtract unequal quantities from equal quantities, the results are going to be unequal in the class? Reverse order. If you were to subtract unequal quantities, like 7 and 2, from, so the from comes first, equal quantities, the results will be unequal in the reverse order. Okay? If we were to multiply equal quantities by unequal quantities, if we were to multiply equal quantities by unequal quantities, the results will be unequal in the class? Same order. Multiply equal quantities by unequal quantities, the results will be unequal in the same order. If we were to add unequal quantities to unequal quantities of the same order, if we were to add unequal quantities to unequal quantities of the same order, then the results will be unequal, class, in the same order. If you were to take, for instance, 5 and 2, add a 12 and a 3, you're going to get a 17 and a 5. So add unequals to unequals in the same order, get unequal in the same order. If you were to divide unequals by equals, if you were to divide unequals by equals, the results are going to be unequal in the class? Same order. Start with unequals like 12 and 27 and divide them by equals like 3 and 3. You get 4 and 9, and they'll be unequal in the same order. If you were to divide equals by unequals, if you were to divide equals by unequals, the results are going to be unequal in the class? Reverse order. Take equals like 10 and 10, but divide them by 2 and 5, you get the reverse order. Do you see how to think these through? Again, we could do a lot more of them, but the main thing is just learning how to think through them, make up some numbers, it's whatever numbers pop into your head, and go from there. And again, normally you'll see it written on a page, you'll have a little bit more time to think it through, but do you understand how to reason through them? All right, we'll practice more with those in the days ahead. The last thing we looked at yesterday was a fairly lengthy proof involving a triangle. And we said if you were to know two sides of a triangle, for instance, this is, let's just say 12 inches, and this is, say, 15 inches. I don't know how big the third side is. But with sides of 15 and 12, I know this side has to be at least bigger than what, class? No.
Opposite sides of 15.
It has to be bigger than 3 inches. Because remember, any side of a triangle is greater than the difference. If you were to fold this 15-inch side down, 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 down to where we're right about here, you'd get a third side that's just about 3 inches, right? But at exactly 3 inches, that means the two sides are laying on top of each other, you don't have a triangle anymore. And then as you make this side go up, 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 you make this side get bigger and bigger. But the side at least has to be 3 inches, right? But it must be less than 27 inches. Why must it be less than 27? Well, imagine you took this 15-inch side and folded it out. This side will get bigger and bigger and bigger and bigger until if you folded it completely back, you'd have 27 inches, but you also wouldn't have a triangle anymore. You'd have one straight line, right? But at almost there, you get almost 27 inches. So the biggest a side can be is just barely less than the sum, but it's always greater than the difference. Let's take another triangle. Let's suppose we had a side of 8 centimeters and a side of 24 centimeters. I don't know how big that side is with just that knowledge. Again, the angle makes all the difference in the world. But I do know that side has to be smaller than what, class? It must be smaller than 32 centimeters because any side of a triangle is smaller than or less than the sum. But it must be greater than 16, greater than the difference. Those statements again in your class notes. Make sure we're looking that over. For now, let's go and take a look at your homework handout. Handout 24. If you would hold that up so that I can see that it is completed here in just a second. We'll see how we did on that. All right. Question mark.
Me too.
What?
I started off like 30 minutes looking at it.
All right, as long as you spent ample time thinking it through, I'll take it. Again, I was telling somebody before class, at least about a half hour is what you should expect. Now, sometimes if it just clicks, you're like, I see how to do it. That's awesome. But you ought to plan to spend at least a half hour working on geometry proofs. Make sure you really put the time in. That's how your brain's going to get better. All right, and this is not drawn entirely to scale, but we'll just not trust our eyes, all right? We've got this random quadrilateral. Now, that's a big nothing, okay? No sides parallel that I can see, so it's not a trapezoid, certainly not a parallelogram, but I do know there's two equal sides. AB and BC were given to us as being equal in the given, and then we were told about the other two sides that DC was bigger than AD. So I got two sides here not equal to each other, two sides here that are equal to each other. That should have been your first statement, and of course your first reason class would have just been given. From there I told you, draw AC. So on your picture you should have drawn, as a dotted line, this auxiliary line AC. By the way, what do we call a line like this that joins non-consecutive vertices? A diagonal, right? A diagonal. And we draw this diagonal AC. Of course, the reason we would have used here, class, 2 points to determine a straight line. But I emphasize to you, this forms two different triangles. So I wanted you to kind of look at this as a triangle, and this is a triangle. Another thing is, as soon as you draw this line, you've now taken what was one angle at A and one angle at C, and you've broken them into parts. So a great strategy tip would be to do what here, Audrey?
Number.
Yeah, how did you number your angles?
1, 2, 3, and 4. 3 on the right side.
3 over here?
Yeah.
Nope. That's the left side.
Yeah, left side.
Left side 3 and right side 4. 1, 2, 3, 4? All right, excellent. All right, however you chose to number them is fine with me, 5, 6, 7, 9, whatever you did for your numbers, it really doesn't matter. But as we look at this, we have now got a little bit of clang. Starting out, having two equal sides is not clang, unless they're in a triangle. Then it's clang. So Ethan, what should we have put for number 3? I'm sorry?
Angles.
What angles?
A and C. But we've already just trying to prove. This is where I got stuck at. I saw the two sides equal, I was like equals angles, but then I saw the prove is trying to get angle A greater than angle C. So I got confused there. I was like,
Well, let's just look at this triangle. So ignore everything else you see here. You can just look right here at ABC. What must be true is AB and BC.
Angle 4?
Angle 2 equals angle 4. Now again, your numbering might have been different, but essentially say, I've got two equal angles, however you numbered them. But clang, two equal sides, two equal angles. Reason, angles opposite equal sides in a triangle are equal. How many had those two angles on the right-hand side of the diagonal equal to each other? All right, excellent, all of you. But there's also a clang in the other triangle, because it is in fact clang if two sides are not equal to each other. What's the implication of that, Quentin?
Angle 3
3 is bigger than angle 1 or angle 4?
I'm sorry?
Angle 3 is bigger than angle 1 or angle 4?
Now, are you basing it off these numbers here? Is this where your angle 3 is?
Yeah. Or that's where my angle 4 is.
That's where, okay, so you're saying this angle was your 3? So, so for our purposes, you would say that angle 4 is bigger than angle 3?
Yes. And angle 1.
And bigger than angle 1. How do we know that 4 is bigger than 3 or 1?
Exterior angles.
Oh, careful. Is 4 an exterior angle? It's outside, but remember, an exterior angle would be if one side of the triangle was extended. That would be exterior. Does that make sense? Yeah, so just because it's outside doesn't make it truly exterior unless it's formed by extending a side. Coming back here to this triangle, ADC, right? So kind of ignore everything else here. Unequal sides in a triangle is claim, Chris.
Angles opposite unequal sides, angles opposite unequal sides are unequal. So
Such
therefore,
that the
greater side equals the greater angle.
has the greater opposite angle. So of these two angles, which must be greater, Chris? Angle 1 has got to be bigger than angle 3 because angle 1 is across from the greater side, 3 across from the smaller side. So again, your numbering might have been different, but we should have had angle 1 bigger than angle 3 because if in a triangle two sides are unequal, the angle opposite the greater side is greater than the angle opposite the smaller side. Should have had something along those lines there for number 4. How many had that claim statement in the proof? Okay, a few of you and then a couple of you erasing. Again, watch for those claims. And that's one of the beauties of diagonals is they take a four-sided figure about which we know nothing worthwhile and turns into a couple of triangles about which we definitely know something worthwhile, right? Now, here's the deal. Ultimately, I'm trying to prove, as Ethan pointed out, that A is bigger than C. This is what I'm trying to prove. The problem is, Ethan, I went and took an angle like A that was complete and entire, and I chopped it up. I took an angle like C that was complete and entire, and I chopped it up. So how would we get back to A and C again if I went and chopped these angles up? Because I got these 1s and 2s and 3s, but I just want A and C again, you know? How do I get...
1 plus equals 2, and then angle 3 plus angle 4.
Yeah, angle A is angle 1 plus angle 2. Angle C is angle 3 plus angle 4 because
The whole is equal to the sum of its parts.
the whole is equal to the sum of all its parts, right?
I have that one here.
So if A is the sum of its parts and C is the sum of its parts, and watch, this is analytical thinking now, you ready? If I want to prove that A is greater than C, then I must be able to prove that 1 plus 2 is greater than 3 plus 4. Does that make sense? I must be able to state that the sum of these parts is greater than the sum of those parts if I am to prove that A is greater than C. Is it possible to say that 1 and 2 together have to be bigger than 3 and 4 together? Chris?
Yes.
Why? How?
Because we have that angle 1 plus angle 2, we need it to be greater than angle 3 plus angle 4, right?
Right, we do.
And we have angle 2 equal to angle 4.
Right, so
we
these
know
two are equals,
that
right?
They kind of cancel each other out in a way.
Okay.
And angle 1 is bigger than angle 3. So
Oh.
if angle 1 is bigger than angle 3, angle 2 and angle 4 are equal, then obviously angle 1 plus angle 2 is bigger than angle 3 plus angle 4.
Right, because if equals are added to unequals, the results are going to be unequal in the same order, correct? And that was the axiom 10 I wanted you to use there on number 5 or 6. These two steps could actually be reversed if you wanted them to be. But we needed to say, well, since 2 and 4 are equal, if I added unequals to those, added 1 to 2, and then added 3 to 4, since these are greater and these are equal, if equals are added to unequals, the results are unequal in the same order. And that would be your reason there. You just write out axiom 10. If equals are added to unequals, the results are unequal in the same order. Again, these two statements could be reversed. But since A is 1 plus 2, since C is 3 plus 4, then in place of 1 plus 2 class, we would just put class. In place of 1 plus 2, we would just put A, because that's what A is. And in place of 3 plus 4, we would just put C. So this needed to be your statement 7. Again, these two could be either or. Technically, this statement could fall anywhere between 3 and 6. So as long as you had, yeah, there's actually, these statements actually could all be interchanged except this one. Okay, this one could be either 5 or 6. This one could be anywhere, and then these two had to fall somewhere before this one. So again, a little bit of variety in the ordering of the steps, but otherwise, that's what we were looking for. Did anyone pretty much nail it? Anyone pretty much nail it? Okay, does it make sense now? Question.
What is the reason for angle 7?
Oh, for number 7, yeah, substitution. We just substitute A in for the 1 plus 2 and C in for the 3 plus 4. Substitution. Good question. Sorry, I failed to mention that. Questions on it now? I know, Ethan, you said lots of question marks. Does it make sense now? Just a very methodical. Get your claims in, then think analytically. I'm trying to prove this. Well, what do I know about A? Well, it's that. What do I know about C? Well, it's that. Well, if that's true, then somehow, some way, A got to be the 1 plus 2, right? And C's got to be the 3 plus 4. Oh! 2 and 4 equals, added to 1 and 3, which are unequals, results unequal in the same order. All right, questions now. Yes, sir.
I have a question on this quiz. You want me to see after class got it, or?
Only if you have questions after watching the video yesterday. Yep. All right. Go ahead and set that aside if you want to maybe use the back side of the handout. And turn to page 121. Page 121 in your textbook. We're going to do a few more proofs today as we continue working very diligently on proofs. Really trying to nail this concept of proofs down here. Page 121, looking at number 3, and they give you the picture, which is awfully nice of them. And what are we given about the picture there in number 3? Kendall? All right, so we've got this isosceles triangle. They draw it kind of flat. Y'all see that? ABC, the original triangle, is kind of flat. You could draw it taller if you wanted to. I'm inclined just to go with the way they drew it, kind of a shorter, flatter triangle here. ABC, where we've got AC and BC equal. But then, Kendall said that BC's extended any distance to D. Now, they only extended it a little bit. I suppose we could have extended it a lot bit if we wanted to. But again, let's just extend it a little ways out here to some point, which we'll call D, and then connect D back down to A. All right, so given AC equals BC, BC extended to any point D. And what are we trying to prove here, Kendall? That AD is less than BD. That the line that came down here to A has to be smaller than the extended BD. This is what we're trying to prove. Once you have that down 2 columns, statements, reasons. Yes, sir.
What if you were to say B, like for the proof BD is greater than AD?
That would be perfectly fine. Yeah, his question, in case you couldn't hear it on camera, could I say BD is greater than AD? Yes, it's the exact same thing. So yeah, if you wanted to reverse the inequality, you certainly could. All right, clang, Genesis. Mean I must have in a triangle. All right, what angles have to be equal? Sure. You want to number the angles here and there? All right, so 1, 2, 3, 4. All right. So what angles are equal?
3 and 4.
Are they? If this is perpendicular and they're both right angles, then they'd be equal. It kind of almost looks a little perpendicular-ish, but I don't know that it is, right? It might have just been the way I drew it. But if I've got 2 equal sides, in a triangle?
Side, angle side.
These two sides are equal. If in a triangle two sides are equal, then the
Angles
what angles?
opposite.
Okay, so what are the opposite angles to these two sides?
B and A.
Well, good. The portion of A that is angle 2, right? So we know that angle 2 has to equal angle B because Genesis.
Opposite interior angles of equal alignment.
Opposite angles of equal lines in a triangle are equal. Okay, we'll take it. Angles opposite equal sides in a triangle are equal, but again, opposite angles of equal lines, just specified in a triangle, are equal, so 2 and B are equal. That's about all the claim we got, right? So our synthetic beginning, very limited. Let's switch to the analytic look. I'm trying to prove ultimately that AD is little and BD is big, right? Now, I started by looking at a little triangle down here, but realized I could address the triangle as a whole. Because after all, AD is a side of what is now the bigger triangle. BD is also a side of what is now the bigger triangle, correct? And if I'm trying to prove that I've got a little side and a big side, how might I do that? How can I get a little side and a big side in a triangle?
Can't do exterior angles. Can we?
Would that help me get a little side and a big side?
Maybe.
You're thinking synthetically. I want you to think analytically. You're thinking, what could I do? I don't want to think, what could I do? I want to think, how specifically can I get this? How can I get a little side and a big side?
Well, with the big side and the whole side, the big side angle across from the big side is greater than the angle across from the little side.
Okay, so what you're saying, Ethan, if I could translate, if I want this to be a big side, class, I need to have a big angle across from it. What is the angle across from this big side, Ethan?
Angle A.
The whole angle A, right? So I want this to be a big angle, correct? And then if I want this to be a little side, what angle needs to be little, Ethan?
Angle B.
Angle B needs to be little. So somehow, some way, class, if I can get that angle A is big and angle B is small, then BD will be big and AD will be small. Agreed? All right? How can I get A to be bigger than B? Chris?
So we know that angle 2 equals angle B, right?
Right, these are equal.
So no matter what angle 1 is, it'll be bigger than B.
One will be bigger than B?
Or both of them together will be bigger than B.
Oh, why would both of them together be bigger than B?
Unequals, because they aren't equal, so would it be like unequals added to equals, something like that?
This actually goes way back to one of the first lessons we had in this class. This goes way back.
No, is it the,
His thought process, class, is since 2 and B are equal, A has got to be bigger than B because A has to be bigger than
any of its parts.
any of its parts. Specifically, which part, Chris?
Well, 1, no, B, 2.
2. A has got to be bigger than 2, right? So we know that A is greater than 2 already, class, because
The whole is greater than any of its parts.
right, we're used to saying the whole equals the sum of its parts, but it's also true that the whole is greater than any of its parts. Oh, and if A is greater than 2, but 2 and B are equal, then I could just plug a B in right here for 2, class. That would just be a... So yeah, A is bigger than B. And therefore, AD is smaller than BD because, how might I word this, Audrey? I got a big angle at A and a little angle at B. And so according to Ethan, at least, he says that having this big angle means there's a big side right here, and a little angle means a little side. Is he wrong? You sure about that? He's correct. A big angle means there's going to be a big side, and a little angle means there's going to be a little side. How might I word that? A big side is across from a big angle. Is that always true, Audrey? When specifically, class, is that true? It's true in a triangle. A big side is across from a big angle in a triangle. I don't know if this is a very good way to word it, but it kind of conveys the idea. How about, let's start with if in a triangle. Start with an if, like most of our thoughts do. If in a triangle, two angles are unequal, then the side is greater than there we go. If in a triangle two angles are unequal, then the side opposite the greater angle is greater than the side opposite the smaller angle. Now, how in the world are you going to remember that on a quiz or test or a homework assignment? Because every night you are studying, you are reading these over, you are memorizing these theorems and corollaries, and we've had this one for several weeks, so it should be memorized pretty good by now if you've been studying every night. Though, if you haven't been studying every night, you pretty much got no chance. Oh, maybe that's why I said we gotta study every night. You know, there's a whole different way to do this though. If you don't like the angle method, we could do this without any angles. There's more than one way to, any cat lovers in here? Close your ears. There's more than one way to skin a cat, as the old saying goes. Okay, you can unplug your ears now. All right, so we could do this entire proof without the use of angles if we were to recall something that we talked about in your class notes yesterday, something you wrote down in your class notes yesterday. You see, we formed, by extending this, this side out here, we formed a little triangle, right? And in forming this little triangle right here, we know something about a triangle. We know that any side of a triangle, class, has to be less than the sum of the other two sides. Should have memorized that statement last night as you were studying, or at least started to. We also memorized that any side of a triangle is greater than the difference of the, it sounds like we got some studying to do, difference of the other two sides. Now, let's look at what I'm trying to prove. Let's go purely analytically here. I'm trying to prove AD is little and BD is big, right? Another method of inequality proof is to say, well, I want AD small, correct? AD needs to be little. I don't know how I'm going to get AD littler than BD, but at least I can get AD littler than something, right? It's a good way to start. Let me at least get AD smaller than something, and I know that any side of a triangle is less than the sum of the other two sides. So for starters, we could say, go ahead and draw a line there underneath your proof where you left off, and draw another number 2. Put another number 2. Okay, we're going to keep the given, of course, but totally new number 2. And we can say, well, I at least know that AD is less than the sum of the other two sides of this little triangle here, AC plus CD. Because any side of a triangle is less than the sum of the other two sides, as was proved yesterday. And notice this at least gets AD smaller than something. At least we're not sitting here just staring at a blank piece of paper, or a piece of paper with a drawing and a given on it, right? At least we're getting somewhere, right? In fact, we've got 2/3 of our proof. We've got the AD and we've got the less than symbol, right? we're making progress, all right? The only thing is, right here, it ought to say BD, right? That's what we're going for, right? Put a BD right in that spot. Well, what is BD, class?
BC plus, or CD.
Yeah, BD is BC plus CD. How do we know that? Whole is equal to the sum of its parts. Or whole equals the sum of parts. You're lazy. Here's a little problem though, right? I can't just plug a BD right there, because BD is BC plus CD. This says AC plus CD. Oh man, what? DC equals, Well, yeah, but I already got a CD right there, right? It's just, I can't plug this in because these don't match. Like, these match. It's just BC and AC.
It says it in the proof. AC equals BC.
It says it in the proof?
Or it says it in the given.
Oh, AC equals, so in other words then, what we're saying here is, that you know how here it said AD is less than AC plus CD? Class, I could say AD is less than BC plus CD. Yeah, that's just substitution. Oh, well, if AD is less than BC plus CD, and BD is BC plus CD, then AD is less than BD. Reason? Substitution again. There's another substitution. And a couple of substitutions in there. Another way to approach the proof, just again, just kind of synthetically is, well, what do I know about AD? Nothing. What do I know about BD? Well, I at least know BD is BC plus CD, right? I mean, it might not help, but only for some parts. Oh, well, since BC and AC are equal, then I guess we could also say that BD is AC plus CD. Wait a second. AC plus CD, any side of a triangle is less than the sum of the other two sides. I've got this. A number of ways in which mentally you could approach the proof. Let's look at number 4. Just we'll talk through this one for sake of time. Don't copy anything down on your paper. But we've got this parallelogram with a diagonal AC. And we've got this, this line drawn from B, drawn in such a way that it makes equal segments. So see how we've got AB. We know AC looks like it's bigger, right? But if I were to take this exact same measurement, I could have a couple of equal segments here, couldn't I? Right? And we call that point here E, so that AE and BE are equal to each other. The objective of the proof, prove that this side is bigger than the leftover piece. Prove that the side is bigger than the leftover piece. Well, what do I know about this line right here, class? It is
Diagonal.
It's a diagonal, but it's also chopped up into pieces. So I know that AC is equal to AE plus EC. And I also know that AE and AB are equal. So if I wanted to, well, AC is equal to AB plus EC, correct? It's also true. Ultimately, the goal of the proof, again, is to prove that BC is greater than, less than, greater than EC, right? Well, I need BC bigger than something, right? I need BC bigger than something. I want it bigger than EC, but ultimately I just need it bigger than something, correct? I know that any side of a triangle is always greater than the difference of the other two sides, correct? So I know that BC at least has to be bigger than, as we're looking at this big triangle here, BC at least has to be bigger than AC minus AB, correct? Okay. And, but what is AC? It's AB plus EC. Well, really AE plus EC, but by substitution, AB plus EC. So therefore, we could say we know that BC has to be greater than AB minus, or plus EC minus AB. Thoughts?
Minus the AB and minus the AB's away and you already got the.
Boom, done. So you can use, again, as we put things in class notes, realize we're going to use those things in proofs. Your homework for this evening is to start, if you would, on a new sheet of paper. This is going to be dictated proof. On a new sheet of paper, start by drawing a parallelogram. Call it WXYZ. Homework for tonight is dictated, not on a handout. You're going to start with a parallelogram. Call it WXYZ. I want you to go and draw the diagonal WY. And number your angles, if you would, 1 and 2. We'll put 1 above the diagonal, 2 below the diagonal. Now I'm going to go off an assumption here. I should have told you to draw it this way. How many of you drew your WX longer than your WZ? Your base is long and your side is a little shorter. I think that's typically how we draw it. Let's go ahead and say that that's given to us. Okay, so we're going to be given parallelogram WXYZ, and we're going to be given that WX, the base, is greater than WZ. So if you drew it the other way, redraw it. Okay, make it so the base is longer. We want to prove that if the base is bigger than the side, that the angle up against the side is bigger than the angle at the base. By the way, there have been some of you that will try to say, well, that's an angle bisector. Oh, no, it's not. In fact, we're going to prove it definitely is not. Unless, of course, these were somehow equal. But no, if you've got a longer base than a side, the angle against the side is, in fact, bigger than the angle against the base. That's what we're trying to prove for homework this evening. We'll take a look at that tomorrow. Have a